Today we're going to talk about something a little different in our pre-calculus journey, and that is something called mathematical induction. We've been working with some different types of statements, and when we get to mathematical induction, we're looking at proving that these statements hold for all the numbers that we claim that they hold for. So, like, if you have a statement like S sub n equals 1 plus 2 plus 3 plus n, and then we tell people, hey, that equals n times n plus 1 over 2. We can verify S sub 1, S sub 2, S sub 3, S sub 4, etc. But how do we verify for all n? If n goes to infinity, like, how do we sit there and verify that that's going to work for any possible n that you might want to use? And that's where this induction comes in. So what I'm going to do is I'm going to basically outline the principle of mathematical induction and kind of verbally talk about what it involves, and then I'm going to just go straight into doing some examples. So this is a type of proof. So let's just do the generalized principle of mathematical induction. Okay, so let's let S sub n be a statement. We're used to seeing that concerning the positive integer n. So it's not necessarily a sum in this case. We're using S sub n now just to be some kind of statement involving that n. Let J be a fixed positive integer. You might also see like K be used instead of J. Suppose although, yeah, we're going to stick with J. Okay. Suppose that both of the following are satisfied. One, S sub J is true. 2, for any positive integer K, where K is greater than or equal to J, S sub K implies, this is the important key, S sub K plus 1. And if those are both satisfied, then you can say that S sub n is true for all positive integers n, where n is greater than or equal to J. Okay. Now your book starts out with a principle where instead of using J, it uses an S sub 1 and an S and then a K less than equal to N. Yeah, I don't know. I feel like it's confusing if I do that to first and then do this second. So I just wanted to go ahead and use the generalized principle. But what does all this mean? You might be looking at that and going, well, that's a lot of mathematical statement there, but what are they talking about? What does this mean? Okay, so with mathematical induction, like I said earlier, you'll have some statement. You can always plug in like n equals 1 and show, hey, this works. N equals 2, show, hey, this works. N equals 3, show, hey, this works. But we need to be able to show it's going to keep working on down the line. If you keep traveling forward with your n's, how can you show definitely that this will work no matter how far forward you travel? So we're going to start with an assumption. We'll use a letter like K. We'll start the assumption that K works, and then we're going to demonstrate that K plus 1 works. Because if we rely on the hypothesis that K works, and we can demonstrate that K plus 1 works, then that's telling us that into the future, K plus 1 into the future, it's going to work. So no matter what K you pick, K plus 1 will always work. So you're showing that the next step will happen, no matter what that next step may be. And notice that we're using a variable and not an actual, like a number. So, it's saying, like, you can pick anything for K. Let's say K is 8. So if you say that, well, K plus 1 or 9 works, great. You can pick any K. You can pick a bigger one, 20. K plus 1, 21 works. So that's what we're basically trying to do. Your book describes it as like dominoes falling or like climbing a ladder. I don't know. I'm not sure I like those analogies, but you're basically trying to look into the future. Will this work down the line? I think of train tracks more like, all right, the train's here on the tracks now and it works, but 100 feet ahead, is it going to work? So the K plus 1 is going to verify, 100 feet ahead is still going to work, no matter where you're at on the tracks. So, okay. So here's some generalized like steps. This is probably where it's going to make a little more sense. We are going to tackle these by first verifying that, we need to prove S sub n. Usually we're going to need to prove something like S sub n is true for every positive integer n, or something like that. And so then we'll verify that S sub 1 actually works. We have to have a starting point. We have to say, okay, this is where we're at. This is where the beginning was. Make sure that works. Sometimes you're not going to use S sub 1. Sometimes you're going to have to use another number. And that's where that J was coming in the definitions earlier. We'll get to that. We'll do an example. So you're basically going to, when I say S sub 1, you're verifying the very first possibility that, if they say n has to be greater than or equal to 3, you verify S sub 3. Okay, so then you write out S sub k to see what it looks like. So see how it should look. Because when you're doing your proof, then you're going to need to know how that looks. And then you're going to need to also write S sub k plus 1. How does it look? So right now you're just kind of doing a little reconnaissance. Like, all right, this is how this one looks. And then if S sub k plus 1 works, this is how it should turn out. This is how it should look. And then we get to the business of we'll assume that S sub k is true. So that's our induction hypothesis. And sometimes in your proofs, you're going to have to use S sub k in order to come to your conclusion that, yes, something worked. Then you're going to use algebra in some way. That's the tricky part. This is the tricky step. Sometimes you have to start recognizing patterns or find clever ways to manipulate things. But use algebra to change S sub k to s sub k plus 1. And if you can successfully do that, if you can use algebra to change s sub k to s sub k plus 1, then you've proven that it works. So then you write a conclusion and tell people, hey, this works based on, my findings here, based on my process. And there you go. And that's it. So the trickiest step is this using algebra step, because that's the one you're going to have to use a little creativity. And sometimes it's going to be a matter of, looking at enough problems and starting to recognize patterns of things to try. That's proofs. It's a lot of just starting to recognize different possible approaches and then going, all right, this type of problem, let me try this approach. Okay. So, and that's basically what I need to say about it, to say what we're going to be doing. So let's get down to business and do one. All right, let A denote a real number. And we're going to define positive integral powers of A as follows. A to the first power is just A. A squared is A times A. A cubed we're going to define as A squared times A, and so on. So that eventually, if you get to A to the n plus 1, that's A to the n times A. Okay, so that's a definition that we're going to use. So that's not what we're trying to prove yet. We're trying to prove that A to the m times A to the n equals A to the m plus n for all positive integers m and n. Okay, so we're going to focus on n and in this process with induction. So our first step, we're going to verify S sub 1. You need a starting point. You need to make sure that, if you use a 1, that it works. Okay, so S sub 1, you can say A to the m times A to the first. We need to verify that it equals A to the m plus 1. Well, yeah, we can say that by the definition of A to the m plus 1. Okay, so F sub 1 works. So now we write S sub k and assume true. So if we write S sub k, we'll have A to the m, A to the k equals A to the m plus k. Okay, so we're assuming that's true. But what we need to do is find out if down the road S sub k plus 1 is true. So let's write S sub k plus 1 just to see what it would look like. So later on, when we're doing our proof, we'll recognize it. So if we had S sub k plus 1, we'd have A to the m, A to the k plus 1 equals A to the m plus k plus 1. So when we work it out, do our algebra magic, this is what we need to have happen. So apply algebra to see if we can get this result. Okay. So let's see here. What if we take a sub m, a to the m, a to the k plus 1, and let's see, we know a to the k plus 1 just by exponent rules. We can write it as a to the m times a to the k times a to the 1, right? And we can also use the definition up here. A to the n plus 1 equals a to the n times a. So we could take a to the k plus 1 and write it as a to the k times a to the first. All right. But I'm going to go ahead and also group these two together for a minute. But let's see here. We can also assume that the associative property of multiplication. It's nothing saying we can't. We've already got the associative property to work with. That's not what we're trying to prove here, really. So we can assume that. So then we can say, what if we rework this? A to the m times a to the k. Group those together times a to the first. Well, just by multiply, when you multiply with exponents, you can rewrite this as a to the m plus k times a to the first. And then getting back to the whole multiplying exponents, you could say a to the m plus k plus 1. Well, there you go. Remember up here, a to the m times a to the k plus 1 equals a to the m plus k plus 1. So this was like this, and now we can say, if we want, we can say it like this. The associative property for addition. So it worked. We started with the left side, and we were able to use some algebra and get it to look like the right side. So we can then conclude that S sub k implies S sub k plus 1. Together with the fact that S sub 1 is true, remember that starting point, S sub 1, then we can say, so, that implication plus the fact that S sub 1 is true, we can say that S sub n is true for all positive integer values of m and n. And there it is. That's it. Now that's the entire proof. So that is a proof by induction, mathematical induction. Okay, let's do another one. I know this is kind of a new concept for many of you. Okay, so here's another. I've got 4 examples I'm going to do. So here's example number 2. All right, let's say that your S sub n says 2 plus 5 plus 8 plus so on down the line, 3n minus 1 is the same thing as n times 3n plus 1 all over 2. And we want to prove that S sub n is true for every positive integer n. Okay, so the very first thing we're going to do is verify S sub 1. Well, S sub 1, you would have basically on the left 3 times 1 minus 1, which is 2. And that has to equal, on the right, 1 brackets 3 times 1 plus 1 all over 2. Well, 3 plus 1 is 4. 4 times 1 is 4. Divided by 2 is 2. Okay. So yes, if you use 1 in there, it works. So you got to make sure that starting point works. So next, you write S sub k and assume true. So S sub k basically looks the same just with k instead of n. 2 plus 5 plus 8, etc. all the way down the line to 3k minus 1 equals k, parentheses, 3k plus 1 over 2. Now we're going to write S sub k plus 1, because we need to know what it should look like when we start doing our algebra. So S sub k plus 1, you have 2 plus 5 plus 8 plus etc. You've got the 3k minus 1, but then you're adding, then you've got 3 times k plus 1 minus 1. And on the right, that has to equal k plus 1 times 3 times k plus 1 all over 2. So we're going to take what's on the left and work with that to try to make it look like what's on the right. That's, we're going to try to make it all like work out. So it's some lovely algebra. Now let's clean up for a second. Let's note that 3 parentheses k plus 1 minus 1 is the same thing as 3k plus 2. That'll make our lives a little easier. All right. So now for the algebra. So we're going to go back to S sub k plus 1. We know that's 2 plus 5 plus 8, etc., plus 3k minus 1 plus 3k plus 2. So then on the right, we can take what we had originally on the right, k times 3k plus 1 over 2. And also add 3k plus 2. You know how in algebra, like, you add something on one side of an equation, you got to also add it to the other side. That's the idea that I'm applying on this problem. Whatever I added on the left to basically take care of that k plus 1 term, I'm going to add that same exact thing over there on the right. And then I'm going to work the right out to get it to look the way it needs to look. It needs to look like when I wrote that S sub k plus 1 statement and got that situation over there on the right, it needs to look like that. It needs to all work out that way. So I'm going to save myself a little hassle right now, and I am not going to keep writing the left side. I'm going to take the right side and start working with that quite a bit. So I'm going to take the 3k plus 2 and I'm going to make it into a fraction by putting it over 2. So 2 on up top over 2 on the bottom. So 2 times 3k plus 2 over 2. Then I'm going to combine the fractions and see where that gets me. So first I'll do a little distributing. 3k squared plus k over 2 in this fraction. And then 6k plus 4 over 2 in that fraction. We can combine them because they have common denominator. So I have 3k squared plus 7k plus 4 all over 2. I really do need this factored, because if you notice up here, it's k plus 1 times, you know, that whole situation. 3k plus 4, basically. All right, so let's see what happens when we try to factor the numerator. So we can do a 3k, a k. I need a 1 and a 4, or probably a 1 and a 4. Yeah, that'll work. A 1 and a 4, and plus plus. Okay, so far so good. I'm going to put the k plus 1 first, since that's how I had it written earlier. And I'm going to take the 3k plus 4 and recognize, you know, I had it as 3 times k plus 1 plus 1. So I'm going to recognize that I can rewrite 4 as plus 3 plus 1. Which means I can then further factor out 3 times k plus 1, parentheses, and then plus 1, all over 2. So I took this 3k plus 3, factored out a 3, and then still have that plus 1. So now it looks the way, when I originally wrote the k plus 1 statement, it looks just like that. So S sub k implies S sub k plus 1. Did a little algebra to make it, to show it. Together with the fact that S sub 1 is true, S sub n is true for every positive integer n. Okay, 2 more. We want to prove that a over b to the n power equals a to the n over b to the n for every positive integer n. We know that a and b are constants, and we know b is not equal to 0. All right. For this one, we can assume that a to the n times a is the same thing as a to the n plus 1, and b to the n times b equals b to the n plus 1. We can assume that. That's going to be useful. Okay. We need to first verify S sub 1. Well, if we wrote a over b to the first power equals a to the first over b to the first. Well, a over b to the first power is a over b, and a to the first over b to the first is also a over b. So yes, that works. So then we write S sub k and assume true. So a over b to the k equals a to the k over b to the k. Now write S sub k plus 1 just to see what it looks like. So a over b to the k plus 1 equals a to the k plus 1 over b to the k plus 1. Okay, now we got to do our algebra. So let's start with a over b to the k plus 1. Let's see what we can do to work with that. Well, we wrote earlier about we can assume that a to the n times a equals a to the n plus 1. We also verified, a over b, a over b to the first equals 1, a to the first over b to the first. So we can take this and rewrite it as a over b, we're just using multiplication principle, a over b to the k times a over b to the first. It's just, rules for multiplying with exponents. We can use that. And then we can use the induction hypothesis, write s sub k and assume true. We can use that. A over b to the k power is a to the k over b to the k. So we can rewrite this as a to the k over b to the k. Nothing wrong with that. And then we're still multiplying by a over b. Well, since we're multiplying, we can do top times top, bottom times bottom. And we get a to the k plus 1 over b to the k plus 1. And that's what we wanted. That's what we needed. When we wrote s sub k plus 1, that's what we saw we needed there on that right side. So we started with the left side, and we used what we know about multiplying with exponents. So we're trying to prove something about using parentheses and a power with a fraction. So we can use what we know about multiplying, and we can also use our induction hypothesis to work out algebraically and get there. So we can say s sub k implies s sub k plus 1 together with the fact that s sub 1 is true. We can say that s sub n is true for every positive integer n. Okay. Now notice in all of our problems so far, we've been dealing with like positive integers or n greater than or equal to 1. In our situations, we're starting with 1 for our n. But when I wrote out the generalized principle of mathematical induction, we didn't assume that n started with 1 necessarily. And so this next example, you're going to see how exactly to adjust things a bit when n doesn't start with 1. N starts with a different number. But the generalized principle still applies. So last one. Let s sub n represent the statement four to the n is greater than 4n. Show that s sub n is true for all values of n such that n is greater than or equal to 2. So notice they didn't start with 1 because if you plug in 1, it doesn't work. And if it was asking you to prove, if n is greater than or equal to 1, then you would have that example to say no, it doesn't. You can prove that it doesn't work. But they are specifying n greater than or equal to 2 for that domain. So we start out, we don't just verify s sub 1. We're going to verify that s sub n is false for n equals 1. You want to show that, and true for n equals 2. So n equals 2 is like that starting point for us in this because it specified n is greater than or equal to 2. So like if you did s sub 1, 4 to the first greater than 4 times 1, 4 greater than 4. Well, that's false. Now, if it said 4 is greater than or equal to 4, you could say true, but it doesn't say that. It says 4 greater than 4. So that's false. So we just showed that it's not going to work for n equals 1, which is great. Like we wanted to make sure of that, you know, to make sure the original statement's on the right track. So then for s sub 2, we look at that one. That's our starting point in this problem. And we find that 4 squared is greater than 4 times 2. 16 is greater than 8. So there we go. So now we can write s sub k and assume true. So we can say s sub k, 4 to the k is greater than 4 times k for all k greater than or equal to 2. So then we write s sub k plus 1. So 4 to the k plus 1 is greater than 4 times k plus 1. And still you're dealing with k being greater than or equal to 2. So that's what it needs to look like. So now for the algebra. Okay. Going back to 4 to the k being greater than 4k. All right, we're assuming that's true. So we need to somehow work this so that we get 4 to the k plus 1 on the left side. And probably the easiest way to do that is just to multiply by a 4. But what you do on one side, go ahead and do on the other side as well. So on the left side, you can rework that using exponent rules and say 4 to the k plus 1 is greater than, I'm going to write 4 times 4k. But you might be like, wait a minute, this doesn't quite look right. We need a k plus 1 somehow over there on the right. But let's think about something for a second. When you have one of these greater thans, there's this little trick. We need a k, instead of 4 times 4k, we need a 4 times k plus 1, right? Based on our s sub k plus 1. That greater than makes this actually pretty easy. We know that 4k is greater than k plus 1 for all k greater than or equal to 2. Just think about it. If you plug in 2, 4 times 2 is 8, compared to 2 plus 1 is 3. Your multiples, of 4 are always going to be greater than just adding a 1. Multiplying by 4 is going to give you a bigger result than just adding 1 every time. For k equal to 2 on up. So you can do this. 4 to the k plus 1 is greater than 4 times 4k, which is also greater than 4 times k plus 1. Because of that 4k being greater than k plus 1. You're allowed to do that. So then you can clean it up and just say 4 to the k plus 1 is greater than 4 times k plus 1. For all k greater than or equal to 2. So s sub k implies s sub k plus 1 for k greater than or equal to 2. So together with the fact that s sub 2 is true, S sub n is true for every value of n greater than or equal to 2. There you go. All right. Well, that's the last example I wanted to show you for this. A lot of the homework has very similar types of examples, similar types of ways to apply your algebra. I encourage you to read through the lesson because there's a lot of more examples worked out. I did not do the examples that are actually worked out in the book. I used teacher examples. So I encourage you to read through the lesson and see some more examples before you really try to start tackling the homework. But the homework's going to pretty much give you the same kinds of problems as what I just did here. So you're going to be applying the same kinds of principles of algebra to work it out, to get from, you're going to do those same steps. You're going to write your S sub k, write S sub k plus 1 to see what it looks like, and then start trying to apply some algebra to get from S sub k to S sub k plus 1, make it look the way it needs to. And when you can get there and make it look the way it needs to, then you can conclude, hey, this works. All right. Well, I find induction to be enjoyable. I feel like it's a puzzle, and I do hope that you guys enjoy it too. So there you go. Turning you loose. Enjoy. Have fun. See you again soon.